These are notes 11.2, power of hydrogen. Please make sure that you've written your name at the top and the period and that you are set to go. We're going to jump around these notes a little more than other notes in the sense that I'm not going to go so linearly through them. So I hope you can follow along with me. All right. Here you can see a scale, and this scale shows us a lot of different factors. We've already talked about these two polyatomic ions here. H3O, what is that called? Well, that's hydronium. It's a positive polyatomic ion created from water by adding a hydrogen to it. Below that, what do we have? Hydroxide, OH negative. It's another polyatomic ion. It's also created from water. Okay, so in this scale, we're just going to focus right here along this line at first, where we see that the H3O and the OH negative are kind of at equal sizes right here. Okay, and we're going to consider pure water for a moment. Okay, distilled water is pure water. I have a bunch of jugs in the back of the room of distilled water. And in a pure sample of about 1 billion H2O molecules, there's actually about 2 of those H2O molecules that are self-ionizing. What does that mean? Well, self-ionizing is when you have 2 H2O molecules and they come close together, and it just so happens that the electrons have managed to spend so much time around the oxygen, because the oxygen is so electronegative, that it actually rips off one of the hydrogens off of another H2O molecule. Be like ripping the hand off of another passing by molecule. So that extremely electronegative oxygen just happened to get 3 hydrogens, forming a hydronium ion, and then left behind a hydroxide ion that it had amputated the hydrogen off of. And no longer do we call these liquids, we now say that these ions are dissolved inside of the water, so we call them aqueous there. And this is a reversible reaction, and it can undo itself. But what we found is this is a rare occasion. In 1 billion molecules, you're only having 2 of those molecules that are creating that kind of interaction. And if we were to map out the molar concentration, so remember, molarity is looking at moles of a solute over liters of a solution. Okay. And so the solution here is the water with a little bit of hydronium, and then the moles is, we can start off looking at hydronium here, okay? That's a concentration, okay? That's the molarity that we've been talking about in the previous unit, okay? So if I were to look at the concentration of H3O plus, and you can draw brackets here to represent concentration. Anytime I use brackets, that means how concentrated something is. And the way I'm going to represent this is that I've got 1.00 times 10 to the negative 7 moles of H3O hydronium inside of 1 liter of distilled water. So out of that liter of distilled water, I've got a really, really, really tiny number of moles of H3O. Remember, 1.00 times 10 to the negative 7 would be 1, 2, 3, 4, 5, 6, 7. So 0.00000001 moles. It's a really small number, okay? Likewise, as this thing is ionizing down here, if I wanted to create the molar concentration of hydroxide, it would be the same in distilled water, okay? I'd also have negative 7 moles of H3O positive in 1 liter of distilled water. So this is in distilled water, you have this interaction where water is kind of doing this to itself. And up here, I can represent that. I'm going to write right here, I have 10 to the negative 7 molar concentration of hydronium ions. And hydroxide, I have 10 to the -7 molar concentration as well. Okay. This is what we call a neutral substance. And so I'm going to write the word neutral up here. Neutral up here above the distilled water function right here. And this is all happening at an equal rate, okay? Now, just a quick note, hydronium is technically what it is physically existing as inside of the water sample. A lot of, when we're dealing with chemistry, we don't necessarily care about hydronium as much as we just care about the fact that there is an extra hydrogen involved, okay, and that extra hydrogen came from somewhere. So instead of an H2, we have an H3. And so sometimes people will talk about the concentration of hydrogen instead, like an H plus. It means the same exact thing. In chemistry, if I talk about the concentration of hydrogen ions, what I really mean is the concentration of hydronium ions. But people flip back and forth between them. So I'm teaching you hydronium right now, but on the back page, we're going to use a lot of the H plus, and that's just kind of how it is. So when I talk about H plus, just think about technically that's hydronium. So in distilled water, you see those equal amounts, but what happens if I add something like sodium hydroxide? And I add that into the water, and it's going to start ionizing the water. Well, guess what? Those little OH polyatomic ions are going to jump off of the sodium hydroxide, and that's going to increase the amount of hydroxide inside of the water. Well, what that does is that decreases the hydronium because some of the hydroxide starts interacting with the hydronium and turning it back into water. So if you dump a bunch of hydroxide in, you'll increase the hydroxide, and some of that hydroxide will react with the hydronium, turning it back into water and decreasing the hydronium. Okay, so that's what's happening over here. As I'm adding more hydroxide, I'm decreasing the amount of hydronium inside of the sample. Okay, so when I get a smaller number of hydronium, 10 to the -8 molar concentration, so that would be 0, a really small number, okay, of hydronium, I'm actually going to get 10 to the -6 molar here. You might see 6 and think, oh, that's a smaller number. But remember, 10 to the -6 is actually a much bigger number than 10 to the -8. Okay, because 10 to the -6 is 1, 2, 3, 4, 5, 6, 0.000001. Whereas this one's going to be 0.00000001. So anyway, you get this kind of effect here where all of these numbers are going to decrease by a certain power. If I increase the, if I decrease the amount of hydronium to 10 to the -9th molar, that's going to increase this to 10 to the -5th molar. Maybe you can see the pattern here, okay? You'll notice when I have 10 to the -9th and 10 to the -5th, those two numbers add up to 10 to the -14th. If I look here, 10 to the -10th, 10 to the -4th, those two numbers also add up to 10 to the -14th. So does the middle, okay? All of these numbers correspond in the sense that if I add them up, I'm going to get 10 to, or if I combine them, I'm going to get 10 to the -14th. Sorry. So this all happens when I add stuff to water, okay? Water will always be in equilibrium with itself, self-ionizing. But if I add things like a bunch of ions and stuff inside of it, inside of seawater, I'm going to start getting more hydroxide. Or if it rains in a lake, that's going to get a little more hydronium, or urine will also add more hydronium to water. If I add coffee to that water, or pressed tomatoes to the water, okay, all of these products up here, you'll notice are mostly water, but I'm adding things to it to change the concentration of H plus or to change the concentration of H3O. So let's say that I increase it to get 10 to the negative 2 molar. So that's 0.01 molar concentration. Or I could even increase it, whoa, I could increase it all the way to, if I want to look at your stomach, okay, the lemon juice has 0.01 moles of hydronium for every liter of solution. Okay, your stomach has 0.1 or 10 to the negative 1 molar concentration. So that means for every liter of liquid inside of your stomach, you're going to have just 0.1 moles of hydronium. That's really acidic. That's going to break down your food. Okay, battery acid is as high as you can get. That's 10 to the 0 molar, which is just another way of saying 1 mole for 1 liter. Okay, so this is like pure hydronium by this point. Okay, and it's you get hydrochloric acid involved over here that's making it like that. Okay, so that's a really highly concentrated molar solution. Okay, if we go all the way up to the top, I can get a really small amounts of H3O inside of things like ammonia, and then you get to 10 to the negative 12 M. Bleach has about 10 to the negative 13 molar, and lye has about 10 to the negative 14 molar. Okay. Now, these numbers are kind of complicated. I don't want, every time that I want to talk about the number or the amount of H plus or hydronium inside of a solution, I'm not going to walk up and say, hey, I have 1.00 times 10 to the negative 8 moles of hydronium per liter of seawater. Isn't that great? That'd be really hard to say. And so scientists have made a scale where they took the numbers, the exponents here, and we didn't want to talk about negatives either. So we turned them into positive numbers and we said, let's make a scale where I turn this 10 to the negative 14 into just scale 14, scale 13, 12, 11, 10, 9. Go ahead and fill that out. Okay, distilled water's at 7, rain milk and peas at 6, coffee's at 5, tomato juice is at 4, vinegar and Coca-Cola's at 3, lemon juice is at 2, stomach acid's at 1, and battery acid is at 0. Okay, this is what we call pH, the power of hydrogen. Okay, if my H plus is at a 10 to the negative 1, I can just take the power that that 10 is raised to and invert it to get a 1. So this is my power of hydrogen, my pH scale that I have. You're probably already familiar with the pH scale. Maybe you've learned it in middle school science, 0 through 14. Okay, but now you kind of understand why we have those numbers, and it has to do with the concentration of H plus and OH negative. Anything below 7 has so many protons floating around in there and becoming hydroniums. Okay, we call those acids. So that's where the pH is less than 7. Okay, those are my acids. And over here, we have our bases. And bases have a pH that is more than 7. That means that our neutral solution is a pH of 7. Okay. Well, that's the pH system. You may not have heard of the pOH system, but there is another scale that is pOH, and it's exactly the opposite. So I'm looking at the power of hydroxide. If the power of hydrogen is 10 to the 0, molar, really concentrated, there's no hydroxide. It's so small, it's like 10 to the negative 14th. I mean, it's so tiny. Well, we'd call that scale 14, scale 13. Okay, so my pOH is going to be the opposite of what my pH scale was. So let's go ahead and fill this in. 3, 2, 1, 0. Okay, so this, you'll notice how we can easily add up the numbers. If my pH is 4, I know that 14 is what they should add up to. So I know that pOH is going to be 10. Or if I know that my pH is 8, well, 14 minus 8 is 6, so my pOH is going to be 6. So they all are going to add up to 14 on either side. And that's what's happening here, okay? So, if we look down here, if I add up HCl, that's going to increase. So I add up hydrochloric acid, like in the stomach, that's going to increase my pH. Sorry, that's going to decrease my pH, but increase my pOH. We kind of talk in reverse. So if I'm decreasing my pH, that means that I'm actually increasing the concentration of hydrogen. I know that's a little bit confusing, but it just has to do with the fact that we're using negative exponents to talk about where my decimal place is. And so that's why that's like that. Okay, so that is the pH scale. And you can kind of see these different substances here that will contribute and add either hydroxides or add hydrogen ions to a solution. All right, we'll pause. If you have any questions, you can ask those now, or if you need to go back. All right, let's move to the back page. All right, this is how you will be able to calculate the relationship between pH, pOH, the concentration of hydrogen ions, and the concentration of hydroxide ions in a solution. So in an aqueous solution. Okay. So, like I said, the pH is the positive version of the exponent on the 10 in the molar concentration of hydrogen ions or hydronium ions. And we're just going to switch to talking about H plus because it's the H plus that when you add that to the solution, it creates more hydronium. So we're just going to talk about H plus now. Okay. So we're going to use logarithms to indicate pH. I'm hoping you know what a logarithm is from math class. We'll just do a quick review here. Okay, a logarithm, log, is simply the power to which 10 must be raised to give the number that we're talking about. So for instance, if I say I have 10 to the negative 2 power, okay, that's the same thing as 0.01. So if I raise 10 to the negative 2 power, that means I'm going 1, 2 over with my decimal place, and I'm going to get 0.01. If I want to express that in terms of log, basically log is going to give me this number. Log is telling me what my exponent is. Now for pH, I don't want negatives because remember, scientists don't like talking, they don't like to be so negative. We'd rather be positive with our outlook on life. So if I want to know what the positive version of this number is, I'm actually going to take a negative log. And what I put after the log is always the number, like the actual numerical value that this whole thing represents. So if I say negative log of 0.01, then that is going to equal 2. If I were to say log of 0.01, then that would equal negative 2. But I'm doing a negative log to get rid of the negative number, okay? Log, sometimes we put a little 10 down here, and we're just saying, like, the number 10 is kind of already embedded inside of the word log, which actually, it's kind of nice that L and O, in my mind, kind of look like a 10 already, like it's a 10G. Okay, so just think about the 10 is already inside of there. Whenever you think of log, you should always be thinking about there's an exponent above a 10. Okay, so when I read this, I'm saying what is the negative version of the number that must be power of 10 to get me 0.01. And negative version of a negative number is the positive, so we get a 2. All right, if that's confusing, well, you're in luck because your calculators should have a little key on your calculator that says log. So at this point, I want you to pull out your calculator out of your bag. And if you don't have a calculator, you can borrow one from the counter. And I want you to see and find the key that says log. Okay. When you press that, it should hopefully give you log in a parentheses. So why don't you just go ahead and type in 0.01 in parentheses. It should give you -2. Well, find the negative sign, put negative log 0.01, and that should give you 2. So use your calculator to your advantage. How do we use logs? Well, pH is equal to the negative log of the concentration of hydrogen. So if my concentration of hydrogen is 10 times to the -2 power molar, then all I got to do is stick that number into here, and that's going to give me the pH, or a pH of 2, which is the lemon juice kind of concentration of hydrogen. Okay, POH is the same thing, but with the concentration of hydroxide. Okay, I can reverse that. So H plus, the concentration of hydrogen ions, is just equal to 10 to the negative pH. So if my pH is 2, then that means that H plus is equal to 10 to the -2 molar. Okay. Another equation here, okay, pH and POH, when you add those together, it always gives you 14. We already talked about that. Okay, and if I take the hydrogen ions, the concentration of hydrogen ions and the concentration of hydroxide ions, I'm always going to get 1.0 times 10 to the -14th. Remember, 14 is kind of that special number. And so if I add up, or sorry, if I multiply 10 to the -6, 10 to the -8, remember to multiply 10 with the power, you're actually just adding the powers. And so you should get 1.0 times 10 to the -14. All right, these equations, I'm going to be providing them on the test and the quizzes. So you don't have to memorize these, but your goal is to be able to use them. So you're going to have to practice using these equations. Let's look at an example with 3 different solutions. This is a table. It might look a little complicated, but let me just break it down. Everything in this column is showing me concentration of hydrogen ions, or hydrogen ions, inside of the orange juice, the beer, the dish soap. Here's the concentration of hydroxide in those solutions. Here's the pH. Here's the POH. And then here's how we have to decide if it's an acid or a base. Okay, so this table's, we're going to fill this out for each of these substances. So let's look over here at my orange juice. Okay, what is the information that I know? Well, I've got 3.2 times 10 to the -4th molar concentration of hydrogen ions. Notice how that's kind of a messy number. I don't just say 10 to the -4. And that's because these up here are kind of estimates. Like lemon juice isn't exactly 10 to the -2. It's actually going to be some number times that, like maybe 1.2 times 10 to the -2. Okay, so these numbers are going to look a little more complicated than just 10 to the -4. We actually have scientific notation. Okay, the hydroxide is going to be the inverse of that. So I've got 3.1 times 10 to the -11th. Okay, I want to be able to find the pH and the POH. How can I solve that? Well, I know my equation for finding pH is equal to the negative log of H plus, the concentration of H plus. And I already know what the concentration of H plus is. So all I need to add to my calculator is negative log 3.2 times 10 to the negative 4. You can go ahead and add that into your calculator now. Now, you can do 3.2e negative 4 as a reminder. So a way to do that would be, oh, that's way too thick. 3.2e negative 4 would be another way to type that in. Okay, you should have gotten 3.49. That's the pH. How do I find the POH? Well, you could do negative log of a concentration of OH negative, or you could also do the easy way, POH plus pH equals 14. So all you need to do is 14 minus 3.49. What is that? You should have gotten 10.51. Okay. Now I want to know, is this an acid or a base? I like to look at the pH. I got to remember, if the pH is below 7, it's an acid. If it's above 7, it's a base. Well, it's below 7, so this is an acid. And that makes sense because this is orange juice. It's pretty acidic. All right, let's go down to beer here. Okay, for beer, I'm looking at this row of data and examining the acids and bases. And if you're behind and you need to ask the sub to pause, you can do that. But we're going to look here. Oh, I did not mean to get rid of all those. This. Okay, so my concentration of H plus is missing. So I want to find out what that is. Okay, there's a couple of different equations I could use. I know what my OH negative concentration is. That's going to be maybe a little more complicated. Let me just use, if I can find out what the pH is first, then I can work backwards and find out what the concentration of hydrogen is. So I know what my POH is. POH is 9.70. So all I need to do is take 14 minus 9.70, and that's going to be what my pH is. Go ahead and calculate that on your calculators and write it down. Okay, what is the answer? Or do it in your head. Okay, it's 4.30 is my pH. Okay, so I know that H plus, the concentration of H plus is equal to 10 to the power of negative pH. So all I got to do is do 10 to negative 4.30. Now, at this point, you might be tempted to type into your calculator 1e negative 4.3. And if you do that, you're probably going to get a syntax error. Why? Well, calculators don't like a decimal place after you use the e function. So if there's a decimal place, you don't want to use that. So just use 10 caret negative 4.30. And you don't need to use don't need to put into scientific notation or anything like that. Okay. When you do that, I'll go ahead and give you a chance to do 10 caret negative 4.3. What is your answer? Okay, you should get something like 5.0 times 10 to the negative 5. Your calculator might say 5e negative 5. Okay. Actually, what I can do, I can use 3 sig figs here. So I'm going to say 5.00. Okay. So sorry, we can do a 1 there, 5.01. Okay, times 10 to the negative 5. So that is the concentration of hydrogen ions. And if you want to kind of visualize that, okay, basically what that's equal to is I'm saying 1, 2, 3, 4, 5. So what I'm saying there is 0.00005001 moles of hydrogen ions per liter of the solution is what that's saying. Okay. Now, my last step is I need to figure out, is this an acid or a base? Well, this is below 7, so that means I'm dealing with an acid. So beer is acidic. Not as acidic as orange juice. Orange juice is going to have a higher concentration of H plus of hydronium inside of its solution. All right, let's go to dish soap. This time I have the opposite data because before I was dealing with pH and H plus, and now I need to figure out POH and OH negative. Let's find a different way to deal with this, okay? So I'll start with the simplest thing first. I want to know what is the POH. Okay, my POH is going to be 14 minus 9.20. I could do that. Or if I wanted to do it a little more complicated, and I'll just show you maybe the more complex way here as well so that you can know how to do this, okay? Note that up here, I've got this equation right here, okay? This equation is the concentration of hydrogen ions times the concentration of hydroxide ions is equal to 1.0 times 10 to the negative 14th. Okay, that means I can do a little bit of algebra. So if I want to find out what hydroxide is, I could divide both sides by the concentration of H plus. Okay, H plus, cross that off. So my OH negative is just going to equal 1.0 times 10 to the negative 4th divided by the concentration of H plus. Vice versa with hydrogen, okay? So here, to find out what my OH negative is, I can just take my concentration of H plus, and I can take 1.0 times 10 to the negative 14th, divide that. So in your calculator, you'd type in 1e negative 14 divided by 6.3e negative 10. I'll give you a moment to enter that into your calculator. Right? Well, you should have gotten, we'll round this to 2 sig figs because we got 2 sig figs here, okay, about 1.6 times 10 to the negative 5th. Always make sure whatever, if your calculator gives you a long number, usually at the end it tells you E negative 5 or something like that. Always make sure that you look to see that there's an E at the end. Okay, so that's how many hydroxide ions I have. And I'm, I'll just do a quick check. Okay, this is a very small number. That's a very large number. 1.6 times 10 to the negative 5 in terms of the fact that it's closer to 0 than this one is. Okay, so, sorry, closer. This is a larger value. Okay, so POH is simply the negative log of hydroxide concentration. Okay, so I'm trying to look at what the negative log is. Now you might be tempted, oh, let me just look up here. This is a negative 5, so the negative log must be 5. So maybe you're going to write down 5. Well, hold on there. That would be true if it were 1.0 times 10 to the negative 5, but it's not. It's 1.6 times 10 to the negative 5. So we have to still enter this into your calculator. You're going to enter in negative log 1.6 times 10 to the negative 5, and that's going to do the math for you. I'll give you a moment to enter that in. So you can enter in negative log 1.6 e negative 5. And that should get you it should say 4.79588. You're going to round up to 4.80. Okay. So here, to find out if it's an acid or base, we'll look at the pH. That's 9.2. That's above 7. So this is a base. Soap is a base. All right. So that may have seemed a little bit complicated, but that is going to be okay because you're going to have these equations that you're going to work with. Okay. So you're going to get your homework, and you can practice on your homework these concepts of figuring out the concentration of hydrogen and hydroxide ions inside of solutions that have other things dissolved in them that are manipulating the concentration of those substances. And you can use these equations to, if you know the information of one of them, you can know the information for all the other factors. All right, this was your notes 11.2. Thank you.